Alright, welcome back. This is lecture 14 in this course, Mathematical Tools for Cognitive Science. The topic of this lecture is examples of trigonometric identities. Okay. So, in this lecture, we will practice how to prove trigonometric identities. So, we will take some more examples. So, we will continue from our previous lecture where we introduced some trigonometric identities, and we also saw how to prove a trigonometric identities using the identities that we already know. In this lecture, we will practice some more trigonometric identities. Okay. So, let us begin. So, one of the identity that we have proved in the previous lecture is sin 2 theta equals to 2 tan theta divided by tan 1 plus tan square theta. Okay. Now, similarly, there is an identity for cos 2 theta. So, this time let us say rather than proving the identity, let us derive cos 2 theta in terms of tan square theta, and let us see what is the term that we will get. Okay. So, we want to express cos 2 theta in the form of tan square theta. Okay. So, let us try to do this. So, first what we will do, the first step that we took in sin 2 theta, actually you can follow the same steps. So, it would be a good practice. So, the first we will break 2 theta into theta plus theta. Now, we have a function of the form cos theta plus phi. Okay, so, consider another theta as phi. So, what is cos theta plus phi? It is cos theta cos phi minus sin theta sin phi. Okay. So, basically cos theta minus sin theta. So, this would become cos square theta minus sin square theta. Okay. But now we need to get it in form of tan square theta. So, let us apply the same idea that the denominator here is actually 1. So, what if we replace 1 by sin square theta plus cos square theta. Yeah. And now, we divide both numerator and denominator by cos square theta. So, when we divide the, let me write it, we will divide the numerator by cos square theta as well as we divide the denominator by cos square theta. We can do this because we are dividing by same thing, and if this cancel out, we get back the same term. So, when we do this, what we will have here that this cos square theta will cancel out. So, you will have just 1 left here, and on this side you would have sin square theta divided by cos square theta, and this entire thing in the denominator you have sin square theta by cos square theta plus 1. Okay. So, now sin theta by cos theta is tan theta. So, in the numerator you get the term 1 minus tan square theta, in the denominator you get 1 plus tan square theta. Okay. So, that is what you get, 1 minus tan square theta divided by 1 plus tan square theta. So, cos 2 theta is equal to this. Okay. So, let us, so we have derived, so what is sin 2 theta, what is cos 2 theta. What if I ask you to derive what would be tan 2 theta, okay, tangent of 2 theta. Let us see. So, I have not told you what is the identity I think about tan 2 theta, maybe I have not, or if I have, I do not remember. So, we can take a look here. I think I have not, but I have told you identity about tan a plus b. Okay. What if we try to derive this identity? Can we do this? Can we derive this identity, tan theta plus phi equals to tan theta plus tan phi divided by 1 minus tan theta tan phi? Let us give it a try. Yeah. So, rather than tan to theta, let us first derive tan theta plus phi. Now, because its function is tangent function, so you can write it as sine divided by cos, sine theta plus phi, cos theta plus phi. Okay. And now sine theta plus phi is what? Sine theta cos phi plus cos theta sin phi divided by cos theta cos phi minus sin theta sin phi. Okay. This is what you get. Okay. Now, remember we need to get it in terms of 1 minus tan theta tan phi, something like that in the denominator. So, what if you divide by this term, okay, both numerator as well as denominator. So, if you divide the numerator by this term, okay, so sin theta plus cos phi plus cos theta into sin phi divided by cos theta cos phi, and this whole thing is divided by cos theta cos phi minus sin theta sin phi divided by cos theta cos phi. Okay, so, let us see what happens. So, in the numerator cos phi will cancel out. So, you have sin theta by cos theta. So, which is tan theta. Here cos theta will cancel out and you would have sin phi by cos phi. So, basically tan phi. In the denominator cos theta cos phi, this will become 1, and here sin theta sin phi divided by cos theta cos phi would be tan theta tan phi. Okay. Since proved, so we proved this identity, that tan theta plus phi equals to this. Okay. Now, what if you have tan 2 theta? Well, for tan 2 theta, you can rewrite it as tan theta plus theta. So, that would be tan theta, I am just applying this identity now, tan theta divided by 1 minus tan theta into tan theta. So, you get 2 tan theta divided by 1 minus tan square theta. By the way, can you write it in form of sine and cos? Okay. This is right now in form of tan theta, but can you write it in form of sine and cos? Yes. So, let us write what would be 2 tan theta? It would be 2 sin theta divided by cos theta, and in the denominator you would have sin square theta by cos square theta. Okay. So, it turns out that the numerator would remain 2 sin theta by cos theta, and denominator you would have cos square theta minus sin square theta divided by cos square theta. Okay. Now, you can take cos square theta in the numerator, 2 sin theta by cos theta into cos square theta, and in the denominator you would be left with cos square theta minus sin square theta. So, this would give you, this cos theta will cancel out one of the cos theta. So, you would be left with 2 sin theta cos theta divided by cos square theta minus sin square theta. Okay. This is what you will get. Okay. Now, this is also an expansion of, the numerator is expansion of sin 2 theta, denominator is actually cos 2 theta, that is why it is equal to tan 2 theta. But this is what you get in terms of sin theta cos theta. Do you want to see why sin 2 theta is this? Well, sin 2 theta can be written as sin theta plus theta, which is sin theta cos theta plus cos theta sin theta. So, that means it is 2 sin theta cos theta, okay, and so on for cos 2 theta as well, right. So, this is how you can do this. Okay. Now, let us try one more identity. So, let us say you have this tan square x divided by 1 plus tan square x, and you have to prove that this is equal to sin square x. By the way, it is not necessary that you use theta every time, because that is just an input variable. You can use x as well. It is just that x or theta would take values in radians, basically, which would be a set of real numbers. Okay, let us do this. So, we need to prove this is equal to sin square x. So, let us try to break it in terms of sin by cos. Let us try to break tan square in terms of sin square cos square, because you need to reach sin square. So, the LHS can be written as sin square x divided by cos square x, and this whole thing is divided by 1 plus sin square x by cos square x. Okay. Now, in the numerator, let us keep sin square x by cos square x. Let us try to solve the denominator term, which would become cos square x plus sin square x divided by cos square x. Okay. Now, here you are getting cos square x in both the denominators. So, this will cancel out. So, numerator you are left with sin square x, in the denominator you are left with cos square x plus sin square x. Now, you know that this is equal to 1. So, basically this thing is equal to sin square x, and it is proved. Okay. So, this is how you can solve this particular identity. Okay. What else? Let us try something more. Let us try these. 1 minus 2 cos square x is equals to tan square x minus 1 tan square x plus 1. Okay, we will try to solve this one now. You will try to prove this identity. You can try it, you can pause the video and try it yourself, or you can walk with me. So, this is left hand side, 1 minus 2 cos square x. Okay. We need to take it in the form of tan square x, right. So, how do we get it in the form of tan square x? So, one approach that we have applied in some of the previous problems was this, that you divide basically in the denominator, because you have 1. So, you replace 1 by sin square x plus cos square x. Okay, fair enough. And now, can we divide it by cos square x? Let us see. So, if you divide this entire thing by cos square x, so in the denominator you will get 1 minus 2 cos square x by cos square x. In the denominator you will get sin square x by cos square x tan square x plus 1. So, we have got the desired denominator, which is tan square x plus 1. The denominator needs some work here. So, the denominator looks something like this. It is 1 by cos square x minus 2. Numerator remains 1 plus tan square x. Okay. So, is there a way to simplify this? We need to get the form 1 minus tan square x minus 1. Yeah. So, one thing we can try here is that, can we write, okay, so can we write this 1 as sin square x? Okay, let me write on the bottom line. So, I am replacing this 1 by sin square x plus cos square x, and this whole thing is divided by cos square x minus 2. In the denominator we still have 1 plus tan square x. Okay. What this will do? Well, because of this, what you will get in the numerator tan square x plus 1, right. You divide this. So, this is tan square x plus 1 minus 2 divided by 1 plus tan square x. So, in the numerator you will have then tan square x minus 1, then 1 plus tan square x. So, hence you have proved this identity as well. So, this is how you can solve these problems on trigonometric identities. Okay. So, using some existing identities about sine and cos, you can solve some more identities. So, this is a good practice because this way you learn how to apply these sine, cos and tan functions. Right. But just to recap, the important part in trigonometric functions is that these are periodic functions. Sine function looks like this, cos function has a value 1 here and goes quite opposite like this, right. And tan function actually it is defined in intervals between minus pi by 2 to pi by 2 like that. So, these are periodic functions, they repeat their values after certain interval. So, there are some interesting properties. Sine function is an odd function, cos function is an even function, right. And importantly, if let us say you have something that is rotating, so you can determine the height of the rotating end as it changes with reference to some ground as a function of angle, right. So, these are all functions which take angle as an input and gives you some properties of the rotating end as the output. Okay. So, trigonometric functions are actually have huge applications in physics and many fields. In cognitive science, they might have limited applications, but they have good set of applications in at least in when you want to model dynamic systems which involve some phase changes. For example, when you want to develop some model of eye tracker, eye tracking and reading, right, that is where these functions are important. Okay. So, I will suggest that you practice with these identities. So, you get used to, so that you get used to these functions and you can draw, you can also get used to drawing the graph of these functions. Okay. Now, in the next lecture, I will take one remaining topic in trigonometric functions, which is how do we represent a point in a two-dimensional plane using these trigonometric functions. And then I will wrap up with some more practice problems on trigonometric functions, right, and a couple of applications it would have in cognitive science or any related fields. Okay. So, all right. So, I will stop here for this lecture and see you in the next lecture for the last part of this entire module on functions. Okay. All right. Thank you.